The de Broglie-Bohm theory, also known as the pilot wave theory, Bohmian mechanics, the Bohm or Bohm's interpretation, and the causal interpretation, is an interpretation of quantum theory. In addition to a wave function on the space of all possible configurations, it also postulates an actual configuration that exists even when unobserved. The evolution over time of the configuration is defined by the wave function via a guiding equation. The evolution of the wave function over time is given by Schrödinger equation. The theory is named after Louis de Broglie and David Bohm. The de Broglie-Bohm theory is explicitly non-local. The velocity of any one particle depends on the value of the guiding equation, which depends on the configuration of the entire universe. Because the known laws of physics are all local, and because non-local interactions combined with relativity led to causal paradoxes, many physicists find this unacceptable. The theory is deterministic. Most variants of the theory that support special relativity require a preferred frame. Variants which include spin and curved spaces are known. It can be modified to include quantum field theory. Bell's theorem was inspired by Bell's discovery of the work of David Bohm and his subsequent wondering if the obvious non-locality of the theory could be eliminated. The theory results in a measurement formalism, analogous to thermodynamics for classical mechanics, that yields the standard quantum formalism generally associated with the Copenhagen interpretation. The measurement problem is resolved by this theory since the outcome of an experiment is registered by the configuration of the particles of the experimental apparatus after the experiment is completed. The familiar wave function collapse of standard quantum mechanics emerges from an analysis of subsystems and the quantum equilibrium hypothesis. Two polls conducted at conferences on the foundations of quantum mechanics in 2013 showed this interpretation to be favored by a significant fraction of the participants. There are several equivalent mathematical formulations of the theory and it is known by a number of different names. The de Broglie wave has a macroscopical analogy termed Faraday wave. Overview: de Broglie-Bohm theory is based on the following postulates. There is a configuration of the universe, described by coordinates, which is an element of the configuration space. The configuration space is different for different versions of pilot wave theory. For example, this may be the space of positions of particles, or, in case of field theory, the space of field configurations. The configuration evolves according to the guiding equation. Where is the probability current or probability flux and is the momentum operator? Here is the standard complex-valued wave function known from quantum theory, which evolves according to Schrödinger's equation. This already completes the specification of the theory for any quantum theory with Hamilton operator of type. The configuration is distributed according to its some moment of time, and this consequently holds for all times. Such a state is named quantum equilibrium. With quantum equilibrium, this theory agrees with the results of standard quantum mechanics. Notably, even if this latter relation is frequently presented as an axiom of the theory, in Bohm's original papers of 1952 it was presented as derivable from statistical mechanical arguments. This argument was further supported by the work of Bohm in 1953 and was substantiated by Vigia and Bohm's paper of 1954 in which they introduced stochastic fluid fluctuations that drive a process of asymptotic relaxation from quantum non-equilibrium to quantum equilibrium. Double-slit experiment. The double-slit experiment is an illustration of wave-particle duality. In it, a beam of particles travels through a barrier with two slits removed. If one puts a detector screen on the other side, the pattern of detected particles shows interference fringes characteristic of waves. However, the detector screen responds to particles. The system exhibits behavior of both waves and particles. If we modify this experiment so that one slit is closed, no interference pattern is observed. Thus, the state of both slits affects the final results. We can also arrange to have a minimally invasive detector at one of the slits to detect which slit the particle went through. When we do that, the interference pattern disappears. The Copenhagen interpretation states that the particles are not localized in space until they are detected, so that, if there is not any detector on the slits, there is no matter of fact about which slit the particle has passed through. If one slit has a detector on it, then the wave function collapses due to that detection. In de Broglie-Bohm theory, the wave function travels through both slits, but each particle has a well-defined trajectory that passes through exactly one of the slits. The final position of the particle on the detector screen and the slit through which the particle passes is determined by the initial position of the particle. Such initial position is not knowable or controllable by the experimenter, so there is an appearance of randomness in the pattern of detection. The wave function interferes with itself and guides the particles in such a way that the particles avoid the regions in which the interference is destructive and are attracted to the regions in which the interference is constructive, resulting in the interference pattern on the detector screen. To explain the behavior when the particle is detected to go through one slit, one needs to appreciate the role of the conditional wave function and how it results in the collapse of the wave function. This is explained below. The basic idea is that the environment registering the detection effectively separates the two wave packets in configuration space. The theory, the ontology of de Broglie-Bohm theory consists of a configuration of the universe and a pilot wave. The configuration space can be chosen differently, as in classical mechanics and standard quantum mechanics. Thus, the ontology of pilot wave theory contains as the trajectory we know from classical mechanics, as the wave function of quantum theory. So, at every moment of time there exists not only a wave function, but also a well-defined configuration of the whole universe. The correspondence to our experiences is made by the identification of the configuration of our brain with some part of the configuration of the whole universe, as in classical mechanics. While the ontology of classical mechanics is part of the ontology of de Broglie-Bohm theory, the dynamics are very different. In classical mechanics, the accelerations of the particles are imparted directly by forces, which exist in physical three-dimensional space. In de Broglie-Bohm theory, the velocities of the particles are given by the wave function, which exists in a 3n-dimensional configuration space, where n corresponds to the number of particles in the system. Bohm hypothesized that each particle has a complex and subtle inner structure that provides the capacity to react to the information provided by the wave function. Also, unlike in classical mechanics, physical properties are spread out over the wave function in de Broglie-Bohm theory, not localized at the position of the particle. The wave function itself, and not the particles, determines the dynamical evolution of the system. The particles do not act back onto the wave function. As Bohm highly worded it, the Schrödinger equation for the quantum field does not have sources, nor does it have any other way by which the field could be directly affected by the condition of the particles. The quantum theory can be understood completely in terms of the assumption that the quantum field has no sources or other forms of dependence on the particles. P. Holland considers this lack of reciprocal action of particles and wave function to be one, among the many non-classical properties exhibited by this theory. It should be noted however that Holland has later called this a merely apparent lack of back reaction, due to the incompleteness of the description. In what follows below, we will give the setup for one particle moving and followed by the setup for particles moving in 3 dimensions. In the first instance, configuration space and real space are the same, while in the second, real space is still, but configuration space becomes. While the particle positions themselves are in real space, the velocity field and wave function are on configuration space, which is how particles are entangled with each other in this theory. Extensions to this theory include spin and more complicated configuration spaces. We use variations of for particle positions while represents the complex valued wave function on configuration space. Guiding equation: for a spinless single particle moving in, the particle's velocity is given. For many particles, we label them as for the th particle and their velocities are given by. The main fact to notice is that this velocity field depends on the actual positions of all of the particles in the universe. As explained below, in most experimental situations, the influence of all of those particles can be encapsulated into an effective wave function for a subsystem of the universe. Schrödinger equation, the one-particle Schrödinger equation governs the time evolution of a complex-valued wave function on. The equation represents a quantized version of the total energy of a classical system evolving under a real-valued potential function on. For many particles, the equation is the same except that and are now on configuration space. This is the same wave function of conventional quantum mechanics. Relation to the Born rule. In Bohm's original papers, Bohm 1952, he discusses how de Broglie-Bohm theory results in the usual measurement results of quantum mechanics. The main idea is that this is true if the positions of the particles satisfy the statistical distribution given by, and that distribution is guaranteed to be true for all time by the guiding equation if the initial distribution of the particles satisfies. For a given experiment, we can postulate this as being true and verify experimentally that it does indeed hold true, as it does. But, as argued in Dar 1/4 RRAL, one needs to argue that this distribution for subsystems is typical. They argue that by virtue of its equivariance under the dynamical evolution of the system, is the appropriate measure of typicality for initial conditions of the positions of the particles. They then prove that the vast majority of possible initial configurations will give rise to statistics obeying the Born rule for measurement outcomes. In summary, in a universe governed by the de Broglie-Bohm dynamics, Born rule behavior is typical. The situation is thus analogous to the situation in classical statistical physics. A low-entropy initial condition will, with overwhelmingly high probability, evolve into a higher entropy state. Behavior consistent with the second law of thermodynamics is typical. There are, of course, anomalous initial conditions which would give rise to violations of the second law. However, absent some very detailed evidence supporting the actual realization of one of those special initial conditions, it would be quite unreasonable to expect anything but the actually observed uniform increase of entropy. Similarly, in the de Broglie-Bohm theory, there are anomalous initial conditions which would produce measurement statistics in violation of the Born rule. But the typicality theorem showed that, absent some particular reason to believe one of those special initial conditions was in fact realized, Born rule behavior is what one should expect. It is in that qualified sense that the Born rule is, for the de Broglie-Bohm theory, a theorem rather than an additional postulate. It can also be shown that a distribution of particles that is not distributed according to the Born rule and evolving under the de Broglie-Bohm dynamics is overwhelmingly likely to evolve dynamically into a state distributed as. See, for example, Ref. A video of the electron density in a 2D box evolving under this process is available here. The conditional wave function of a subsystem. In the formulation of the de Broglie-Bohm theory, there is only a wave function for the entire universe. However, once the theory is formulated, it is convenient to introduce a notion of wave function also for subsystems of the universe. Let us write the wave function of the universe as, where denotes the configuration variables associated to some subsystem of the universe and denotes the remaining configuration variables. Denote, respectively, by and by the actual configuration of subsystem and of the rest of the universe. For simplicity, we consider here only the spinless case. The conditional wave function of subsystem is defined by. It follows immediately from the fact that satisfies the guiding equation that also the configuration satisfies a guiding equation identical to the one presented in the formulation of the theory, with the universal wave function replaced with the conditional wave function. Also, the fact that is random with probability density given by the square modulus of implies that the conditional probability density of given is given by the square modulus of the conditional wave function. Unlike the universal wave function, the conditional wave function of a subsystem does not always evolve by the Schrödinger equation, but in many situations it does. For instance, if the universal wave function factors as, then the conditional wave function of subsystem is equal to. If, in addition, the Hamiltonian does not contain an interaction term between subsystems and then does satisfy a Schrödinger equation. More generally, assume that the universal wave function can be written in the form where solves Schrödinger equation and for all and. Then, again, the conditional wave function of subsystem is equal to and if the Hamiltonian does not contain an interaction term between subsystems and satisfies a Schrödinger equation. The fact that the conditional wave function of a subsystem does not always evolve by the Schrödinger equation is related to the fact that the usual collapse rule of standard quantum theory emerges from the Bohmian formalism when one considers conditional wave functions of subsystems. Extensions, spin. To incorporate spin, the wave function becomes complex vector-valued. The value space is called spin space. For a spin of one-half particle, spin space can be taken to be. The guiding equation is modified by taking inner products in spin space to reduce the complex vectors to complex numbers. The Schrödinger equation is modified by adding a Pauli spin term. Whereas the magnetic moment of the Th particle is the appropriate spin operator acting in the Th particle's spin space, is spin of the particle, and r, respectively, the magnetic field and the vector potential in, is the charge of the Th particle, and is the inner product in spin space. For an example of a spin space, a system consisting of two spin one-half particle and one spin one particle has a wave functions of the form. That is, its spin space is a 12-dimensional space. Curved space. To extend de Broglie-Bohm theory to curved space, one simply notes that all of the elements of these equations make sense, such as gradients and Laplacians. Thus, we use equations that have the same form as above. Topological and boundary conditions may apply in supplementing the evolution of Schrödinger's equation. For a de Broglie-Bohm theory on curved space with spin, the spin space becomes a vector bundle over configuration space and the potential in Schrödinger's equation becomes a local self-adjoint operator acting on that space. Quantum field theory. In DAR 1/4 RRAL, the authors describe an extension of de Broglie-Bohm theory for handling creation and annihilation operators, which they refer to as Bell-type quantum field theories. The basic idea is that configuration space becomes the space of all possible configurations of any number of particles. For part of the time, the system evolves deterministically under the guiding equation with a fixed number of particles. But under a stochastic process, particles may be created and annihilated. The distribution of creation events is dictated by the wave function. The wave function itself is evolving at all times over the full multi-particle configuration space. Hrvoj Nicolia introduces a purely deterministic de Broglie-Bohm theory of particle creation and destruction, according to which particle trajectories are continuous, but particle detectors behave as if particles have been created or destroyed even when a true creation or destruction of particles does not take place. Exploiting non-locality, Anthony Valentini has extended the de Broglie-Bohm theory to include signal non-locality that would allow entanglement to be used as a standalone communication channel without a secondary classical key signal to unlock the message encoded in the entanglement. This violates orthodox quantum theory, but it has the virtue that it makes the parallel universes of the chaotic inflation theory observable in principle. Unlike de Broglie-Bohm theory, Valentini's theory has the wave function evolution also depend on the ontological variables. This introduces an instability, a feedback loop that pushes the hidden variables out of subquantal heat death. The resulting theory becomes nonlinear and non-unitary. Relativity. Pilot wave theory is explicitly non-local. As a consequence, most relativistic variants of pilot wave theory need a foliation of spacetime. While this is in conflict with the standard interpretation of relativity, the preferred foliation, if unobservable, does not lead to any empirical conflicts with relativity. The relation between non-locality and preferred foliation can be better understood as follows. In de Broglie-Bohm theory, non-locality manifests as the fact that the velocity and acceleration of one particle depends on the instantaneous positions of all other particles. On the other hand, in the theory of relativity, the concept of instantaneousness does not have an invariant meaning. Thus, to define particle trajectories, one needs an additional rule that defines which space-time points should be considered instantaneous. The simplest way to achieve this is to introduce a preferred foliation of space-time by hand, such that each hypersurface of the foliation defines a hypersurface of equal time. However, this way is not the only way. It is also possible that a rule which defines instantaneousness is contingent, by emerging dynamically from relativistic covariant laws combined with particular initial conditions. In this way, the need for a preferred foliation can be avoided and relativistic covariance can be saved. There has been work in developing relativistic versions of de Broglie-Bohm theory. See Bohm and Hiley, The Undivided Universe, and 3, 4, and references therein. Another approach is given in the work of Darwin Corter in which they used Bohm-Dirac models and a Lorentz invariant foliation of spacetime. Initially, it had been considered impossible to set out a description of photon trajectories in the de Broglie-Bohm theory in view of the difficulties of describing bosons relativistically. In 1996, Pythagoras had presented a relativistic quantum mechanical description of spin 0 and spin 1 bosons starting from the Duffner-Kemmerer-θ equation, setting out Bohmian trajectories for massive bosons and for massless bosons. In 2001, Jean-Pierre Vigier emphasized the importance of deriving a well-defined description of light in terms of particle trajectories in the framework of either the Bohmian mechanics or the Nelson stochastic mechanics. The same year, Gauss worked out Bohmian photon trajectories for specific cases. Subsequent weak measurement experiments yielded trajectories which coincide with the predicted trajectories. Chris Dewdney and G. Horton have proposed a relativistically covariant, wave-functional formulation of Bohm's quantum field theory and has extended it to a form that allows the inclusion of gravity. Nicolia has proposed a Lorentz covariant formulation of the Bohmian interpretation of many particle wave functions. He has developed a generalized relativistic invariant probabilistic interpretation of quantum theory, in which is no longer a probability density in space, but a probability density in spacetime. He uses this generalized probabilistic interpretation to formulate a relativistic covariant version of de Broglie-Bohm theory without introducing a preferred foliation of spacetime. His work also covers the extension of the Bohmian interpretation to a quantization of fields and strings. Results: below are some highlights of the results that arise out of an analysis of de Broglie-Bohm theory. Experimental results agree with all of the standard predictions of quantum mechanics insofar as the latter has predictions. However, while standard quantum mechanics is limited to discussing the results of measurements, de Broglie-Bohm theory is a theory which governs the dynamics of a system without the intervention of outside observers. The basis for agreement with standard quantum mechanics is that the particles are distributed according to. This is a statement of observer ignorance, but it can be proven that for a universe governed by this theory, this will typically be the case. There is apparent collapse of the wave function governing subsystems of the universe, but there is no collapse of the universal wave function. Measuring spin and polarization, according to ordinary quantum theory, it is not possible to measure the spin or polarization of a particle directly. Instead, the component in one direction is measured. The outcome from a single particle may be 1, meaning that the particle is aligned with the measuring apparatus, or -1, meaning that it is aligned the opposite way. For an ensemble of particles, if we expect the particles to be aligned, the results are all 1. If we expect them to be aligned oppositely, the results are all -1. For other alignments, we expect some results to be 1 and some to be -1 with a probability that depends on the expected alignment. For a full explanation of this, see the Stern-Gerlach experiment. In de Broglie-Bohm theory, the results of a spin experiment cannot be analyzed without some knowledge of the experimental setup. It is possible to modify the setup so that the trajectory of the particle is unaffected, but that the particle with one setup registers as spin up while in the other setup it registers as spin down. Thus, for the de Broglie-Bohm theory, the particle's spin is not an intrinsic property of the particle, instead spin is, so to speak, in the wave function of the particle in relation to the particular device being used to measure the spin. This is an illustration of what is sometimes referred to as contextuality, and is related to naive realism about operators. Measurements, the quantum formalism, and observer independence. De Broglie-Bohm theory gives the same results as quantum mechanics. It treats the wave function as a fundamental object in the theory as the wave function describes how the particles move. This means that no experiment can distinguish between the two theories. This section outlines the ideas as to how the standard quantum formalism arises out of quantum mechanics. References include Bohm's original 1952 paper and R1/4 Collapse of the wave function. De Broglie-Bohm theory is a theory that applies primarily to the whole universe. That is, there is a single wave function governing the motion of all of the particles in the universe according to the guiding equation. Theoretically, the motion of one particle depends on the positions of all of the other particles in the universe. In some situations, such as in experimental systems, we can represent the system itself in terms of a de Broglie-Bohm theory in which the wave function of the system is obtained by conditioning on the environment of the system. Thus, the system can be analyzed with Schrödinger equation and the guiding equation, with an initial distribution for the particles in the system. It requires a special setup for the conditional wave function of a system to obey a quantum evolution. When a system interacts with its environment, such as through a measurement, the conditional wave function of the system evolves in a different way. The evolution of the universal wave function can become such that the wave function of the system appears to be in a superposition of distinct states. But if the environment has recorded the results of the experiment, then using the actual Bohmian configuration of the environment to condition on, the conditional wave function collapses to just one alternative, the one corresponding with the measurement results. Collapse of the universal wave function never occurs in de Broglie-Bohm theory. Its entire evolution is governed by Schrödinger equation and the particles' evolutions are governed by the guiding equation. Collapse only occurs in a phenomenological way for systems that seem to follow their own Schrödinger equation. As this is an effective description of the system, it is a matter of choice as to what to define the experimental system to include, and this will affect when collapse occurs. Operators as observables. In the standard quantum formalism, measuring observables is generally thought of as measuring operators on the Hilbert space. For example, measuring position is considered to be a measurement of the position operator. This relationship between physical measurements and Hilbert space operators is, for standard quantum mechanics, an additional axiom of the theory. The de Broglie-Bohm theory, by contrast, requires no such measurement axioms. In particular, the usual operators as observables formalism is, for de Broglie-Bohm theory, a theorem. A major point of the analysis is that many of the measurements of the observables do not correspond to properties of the particles. They are measurements of the wave function. In the history of de Broglie-Bohm theory, the proponents have often had to deal with claims that this theory is impossible. Such arguments are generally based on inappropriate analysis of operators as observables. If one believes that spin measurements are indeed measuring the spin of a particle that existed prior to the measurement, then one does reach contradictions. De Broglie-Bohm theory deals with this by noting that spin is not a feature of the particle, but rather that of the wave function. As such, it only has a definite outcome once the experimental apparatus is chosen. Once that is taken into account, the impossibility theorems become irrelevant. There have also been claims that experiments reject the Bohm trajectories, 5, in favor of the standard QM lines. But as shown in 6 and 7, such experiments cited above only disprove a misinterpretation of the de Broglie-Bohm theory, not the theory itself. There are also objections to this theory based on what it says about particular situations usually involving eigenstates of an operator. For example, the ground state of hydrogen is a real wave function. According to the guiding equation, this means that the electron is at rest when in this state. Nevertheless, it is distributed according to a no contradiction to experimental results is possible to detect. Operators as observables leads many to believe that many operators are equivalent. De Broglie-Bohm theory, from this perspective, chooses the position observable as a favored observable rather than, say, the momentum observable. Again, the link to the position observable is a consequence of the dynamics. The motivation for de Broglie-Bohm theory is to describe a system of particles. This implies that the goal of the theory is to describe the positions of those particles at all times. Other observables do not have this compelling ontological status. Having definite positions explains having definite results such as flashes on a detector screen. Other observables would not lead to that conclusion, but there need not be any problem in defining a mathematical theory for other observables. See Hyman al. for an exploration of the fact that a probability density and probability current can be defined for any set of commuting operators. Hidden variables. De Broglie-Bohm theory is often referred to as a hidden variable theory. Bohm used this description in his original papers on the subject, writing, from the point of view of the usual interpretation, these additional elements or parameters, permitting a detailed causal and continuous description of all processes could be called hidden variables. Bohm and Hiley later stated that they found Bohm's choice of the term hidden variables to be too restrictive. In particular, they argued that a particle is not actually hidden but rather is what is most directly manifested in an observation, though its properties cannot be observed with arbitrary precision. However, others nevertheless treat the term hidden variable as a suitable description. Generalized particle trajectories can be extrapolated from numerous weak measurements on an ensemble of equally prepared systems, and such trajectories coincide with the de Broglie-Bohm trajectories, and thus may seem to be evidence of the existence of the otherwise hidden variables. However, the results of the weak measurements are also consistent with many other interpretations that do not include such trajectories. Heisenberg's uncertainty principle. The Heisenberg uncertainty principle states that when two complementary measurements are made, there is a limit to the product of their accuracy. As an example, if one measures the position with an accuracy of, and the momentum with an accuracy of, then if we make further measurements in order to get more information, we disturb the system and change the trajectory into a new one depending on the measurement set up. Therefore, the measurement results are still subject to Heisenberg's uncertainty relation. In de Broglie-Bohm theory, there is always a matter of fact about the position and momentum of a particle. Each particle has a well-defined trajectory. Observers have limited knowledge as to what this trajectory is. It is the lack of knowledge of the particle's trajectory that accounts for the uncertainty relation. What one can know about a particle at any given time is described by the wave function. Since the uncertainty relation can be derived from the wave function in other interpretations of quantum mechanics, it can be likewise derived, on the de Broglie-Bohm theory. To put the statement differently, the particle's positions are only known statistically. As in classical mechanics, successive observations of the particle's positions refine the experimenter's knowledge of the particle's initial conditions. Thus, with succeeding observations, the initial conditions become more and more restricted. This formalism is consistent with the normal use of the Schrödinger-Dingo equation. For the derivation of the uncertainty relation, see Heisenberg uncertainty principle, noting that it describes it from the viewpoint of the Copenhagen interpretation. Quantum entanglement, Einstein-Podolsky-Rosen paradox, Bell's theorem, a non-locality. De Broglie-Bohm theory highlighted the issue of non-locality. It inspired John Stuart Bell to prove his now famous theorem, which in turn led to the Bell test experiments. In the Einstein-Podolsky-Rosen paradox, the authors describe a thought experiment one could perform on a pair of particles that have interacted, the results of which they interpreted as indicating that quantum mechanics is an incomplete theory. Decades later John Bell proved Bell's theorem, in which he showed that, if they are to agree with the empirical predictions of quantum mechanics, all such hidden variable completions of quantum mechanics must either be non-local or give up the assumption that experiments produce unique results. In particular, Bell proved that any local theory with unique results must make empirical predictions satisfying a statistical constraint called Bell's inequality. Alan Aspect performed a series of Bell test experiments that test Bell's inequality using an EPR-type setup. Aspect's results show experimentally that Bell's inequality is in fact violated, meaning that the relevant quantum mechanical predictions are correct. In these Bell test experiments, entangled pairs of particles are created. The particles are separated, traveling to remote measuring apparatus. The orientation of the measuring apparatus can be changed while the particles are in flight, demonstrating the apparent non-locality of the effect. The de Broglie-Bohm theory makes the same predictions for the Bell test experiments as ordinary quantum mechanics. It is able to do this because it is manifestly non-local. It is often criticized or rejected based on this. Bell's attitude was, it is a merit of the de Broglie-Bohm version to bring this non-locality out so explicitly that it cannot be ignored. The de Broglie-Bohm theory describes the physics in the Bell test experiments as follows. To understand the evolution of the particles, we need to set up a wave equation for both particles. The orientation of the apparatus affects the wave function. The particles in the experiment follow the guidance of the wave function. It is the wave function that carries the faster-than-light effect of changing the orientation of the apparatus. An analysis of exactly what kind of non-locality is present and how it is compatible with relativity can be found in Maudlin. Note that in Bell's work, and in more detail in Maudlin's work, it is shown that the non-locality does not allow for signaling at speeds faster than light. Classical limit, Bohm's formulation of de Broglie-Bohm theory in terms of a classical-looking version has the merits that the emergence of classical behavior seems to follow immediately for any situation in which the quantum potential is negligible, as noted by Bohm in 1952. Modern methods of coherence are relevant to an analysis of this limit. See Ellery et al. For steps towards a rigorous analysis. Quantum trajectory method, work by Robert E. Wyatt in the early 2000s attempted to use the Bohm particles as an adaptive mesh that follows the actual trajectory of a quantum state in time and space. In the quantum trajectory method, one samples the quantum wave function with a mesh of quadrature points. One then evolves the quadrature points in time according to the Bohm equations of motion. At each time step, one then resynthesizes the wave function from the points, recomputes the quantum forces, and continues the calculation. This approach has been adapted, extended, and used by a number of researchers in the chemical physics community as a way to compute semi-classical and quasi-classical molecular dynamics. A recent issue of the Journal of Physical Chemistry A was dedicated to Professor Wyatt and his work on computational Bohmian dynamics. Eric R. Bittner's group at the University of Houston has advanced a statistical variant of this approach that uses Bayesian sampling technique to sample the quantum density and compute the quantum potential on a structureless mesh of points. This technique was recently used to estimate quantum effects in the heat capacity of small clusters n for n to 100. There remain difficulties using the Bohmian approach, mostly associated with the formation of singularities in the quantum potential due to nodes in the quantum wave function. In general, nodes forming due to interference effects lead to the case where this results in an infinite force on the sample particles, forcing them to move away from the node and often crossing the path of other sample points. Various schemes have been developed to overcome this. However, no general solution has yet emerged. These methods, as does Bohm's Hamilton-Jacobi formulation, do not apply to situations in which the full dynamics of spin need to be taken into account. Occam's razor criticism, both Hugh Everett III and Bohm treated the wave function as a physically real field. Everett's many-worlds interpretation is an attempt to demonstrate that the wave function alone is sufficient to account for all our observations. When we see the particle detectors flash or hear the click of a Geiger counter, then Everett's theory interprets this as our wave function responding to changes in the detector's wave function, which is responding in turn to the passage of another wave function. No particle exists, according to that theory. For this reason Everett sometimes referred to his own many-worlds approach as the pure wave theory. Talking of Bohm's 1952 approach, Everett says, in the Everettian view, then, the Bohm particles are superfluous entities, similar to, and equally as unnecessary as, for example, the luminiferous ether, which was found to be unnecessary in special relativity. This argument of Everett's is sometimes called the redundancy argument, since the superfluous particles are redundant in the sense of Occam's razor. Many authors have expressed critical views of the de Broglie-Bohm theory, by comparing it to Everett's many-worlds approach. Many proponents of the de Broglie-Bohm theory interpret the universal wave function as physically real. According to some supporters of Everett's theory, if the wave function is taken to be physically real, then it is natural to interpret the theory as having the same many worlds as Everett's theory. In the Everettian view, the role of the Bohm particle is to act as a pointer, tagging, or selecting, just one branch of the universal wave function. The other branches are designated empty, and implicitly assumed by Bohm to be devoid of conscious observers. H.D. comments on these empty branches. David Deutsch has expressed the same point more acerbically. According to Brown and Wallace, the de Broglie-Bohm particles play no role in the solution of the measurement problem. These authors claim that the result assumption is inconsistent with the view that there is no measurement problem in the predictable outcome case. These authors also claim that a standard tacit assumption of the de Broglie-Bohm theory is unreasonable. This conclusion has been challenged by Valentini, who argues that the entirety of such objections arises from a failure to interpret de Broglie-Bohm theory on its own terms. According to Peter Holland, in a wider Hamiltonian framework, theories can be formulated in which particles do act back on the wave function. Derivations. De Broglie-Bohm theory has been derived many times and in many ways. Below are 6 derivations, all of which are very different and lead to different ways of understanding and extending this theory. Schrödinger-Dinger's equation can be derived by using Einstein's light quanta hypothesis, and de Broglie's hypothesis. The guiding equation can be derived in a similar fashion. We assume a plane wave. Notice that. Assuming that for the particle's actual velocity, we have that. Thus, we have the guiding equation. Notice that this derivation does not use Schrödinger-Dinger's equation. Preserving the density under the time evolution is another method of derivation. This is the method that Bell cites. It is this method which generalizes to many possible alternative theories. The starting point is the continuity equation for the density. This equation describes a probability flow along a current. We take the velocity field associated with this current as the velocity field whose integral curves yield the motion of the particle. A method applicable for particles without spin is to do a polar decomposition of the wave function and transform Schrödinger-Dinger's equation into 2 coupled equations, the continuity equation from above and the Hamilton-Jacobi equation. This is the method used by Bohm in 1952. The decomposition and equations are as follows. Decomposition note corresponds to the probability density. Continuity equation, Hamilton-Jacobi equation. The Hamilton-Jacobi equation is the equation derived from a Newtonian system with potential and velocity field. The potential is the classical potential that appears in Schrödinger-Dinger's equation, and the other term involving is the quantum potential, terminology introduced by Bohm. This leads to viewing the quantum theory as particles moving under the classical force modified by a quantum force. However, unlike standard Newtonian mechanics, the initial velocity field is already specified, by which is a symptom of this being a first-order theory, not a second-order theory. A fourth derivation was given by Darwin Quarter-RRAL. In their derivation, they derived the velocity field by demanding the appropriate transformation properties given by the various symmetries that Schrödinger-Dinger's equation satisfies, once the wave function is suitably transformed. The guiding equation is what emerges from that analysis. A fifth derivation, given by Darwin Quarter-RRAL, is appropriate for generalization to quantum field theory in the Dirac equation. The idea is that a velocity field can also be understood as a first-order differential operator acting on functions. Thus, if we know how it acts on functions, we know what it is. Then, given the Hamiltonian operator, the equation to satisfy for all functions is, where is the local Hermitian inner product on the value space of the wave function? This formulation allows for stochastic theory such as the creation and annihilation of particles. A further derivation has been given by Peter Holland, on which he bases the entire work presented in his quantum physics textbook The Quantum Theory of Motion, a main reference book on the de Broglie-Bohm theory. It is based on three basic postulates and an additional fourth postulate that links the wave function to measurement probabilities. 1. A physical system consists in a spatio-temporally propagating wave and a point particle guided by it. 2. The wave is described mathematically by a solution to Schrödinger wave equation. 3. The particle motion is described by a solution to independence on initial condition, with the phase of. The fourth postulate is subsidiary yet consistent with the first three. 4. The probability to find the particle in the differential volume at time t equals. History. De Broglie-Bohm theory has a history of different formulations and names. In this section, each stage is given a name and a main reference. Pilot wave theory. David de Broglie presented his pilot wave theory at the 1927 Solvay conference, after close collaboration with Schrödinger, who developed his wave equation for de Broglie's theory. At the end of the presentation, Wolfgang Pauli pointed out that it was not compatible with a semi-classical technique Fermi has previously adopted in the case of inelastic scattering. Contrary to a popular legend, de Broglie actually gave the correct rebuttal that the particular technique could not be generalized for Pauli's purpose, although the audience might have been lost in the technical details and de Broglie's mild manner left the impression that Pauli's objection was valid. He was eventually persuaded to abandon this theory nonetheless because he was discouraged by criticisms which it roused. De Broglie's theory already applies to multiple spinless particles, but lacks an adequate theory of measurement as no one understood quantum coherence at the time. An analysis of de Broglie's presentation is given in Bach-Galuppi al. Also, in 1932 John von Neumann published a paper that was widely believed to prove that all hidden variable theories are impossible. This sealed the fate of de Broglie's theory for the next 2 decades. In 1926, Erwin Madelung had developed a hydrodynamic version of Schrödinger's equation which is incorrectly considered as a basis for the density current derivation of the de Broglie-Bohm theory. The Madelung equations, being quantum Euler equations, differ philosophically from the de Broglie-Bohm mechanics and are the basis of the stochastic interpretation of quantum mechanics. Peter A. Holland has pointed out that, earlier in 1927, Einstein had actually submitted a preprint with a similar proposal but, not convinced, had withdrawn it before publication. According to Holland, failure to appreciate key points of the de Broglie-Bohm theory has led to confusion, the key point being that the trajectories of a many-body quantum system are correlated not because the particles exert a direct force on one another but because all are acted upon by an entity mathematically described by the wave function or functions of it that lies beyond them. This entity is the quantum potential. After publishing a popular textbook on quantum mechanics which adhered entirely to the Copenhagen orthodoxy, Bohm was persuaded by Einstein to take a critical look at von Neumann's theorem. The result was a suggested interpretation of the quantum theory in terms of hidden variables I and II, Bohm 1952. It was an independent origination of the pilot wave theory, and extended it to incorporate a consistent theory of measurement, and to address a criticism of Pauli that de Broglie did not properly respond to. It is taken to be deterministic. This stage is known as the de Broglie-Bohm theory in Bell's work, Bell 1987, and is the basis for the quantum theory of motion, Holland 1993. This stage applies to multiple particles, and is deterministic. The de Broglie-Bohm theory is an example of a hidden variables theory. Bohm originally hoped that hidden variables could provide a local, causal, objective description that would resolve or eliminate many of the paradoxes of quantum mechanics, such as Schrödinger's cat, the measurement problem and the collapse of the wave function. However, Bell's theorem complicates this hope, as it demonstrates that there can be no local hidden variable theory that is compatible with the predictions of quantum mechanics. The Bohmian interpretation is causal but not local. Bohm's paper was largely ignored or panned by other physicists. Albert Einstein, who had suggested that Bohm search for a realist alternative to the prevailing Copenhagen approach, did not consider Bohm's interpretation to be a satisfactory answer to the quantum non-locality question, calling it too cheap, while Werner Heisenberg considered it a superfluous ideological superstructure. Wolfgang Pauli, who had been unconvinced by de Broglie in 1927, conceded to Bohm as follows. I just received your long letter of November 20, and I also have studied more thoroughly the details of your paper. I do not see any longer the possibility of any logical contradiction as long as your results agree completely with those of the usual wave mechanics and as long as no means is given to measure the values of your hidden parameters both in the measuring apparatus and in the observe-6 system. As far as the whole matter stands now, your extra wave mechanical predictions unregistered trademark are still a check, which cannot be cashed. He subsequently described Bohm's theory as artificial metaphysics. According to physicist Max Dresden, when Bohm's theory was presented at the Institute for Advanced Study in Princeton, many of the objections were ad hominem, focusing on Bohm's sympathy with communists as exemplified by his refusal to give testimony to the House Un-American Activities Committee. Eventually John Bell began to defend the theory. In Speakable and Unspeakable in Quantum Mechanics, Bell 1987, several of the papers refer to hidden variables theories. Bohmian mechanics, this term is used to describe the same theory, but with an emphasis on the notion of current flow, which is determined on the basis of the quantum equilibrium hypothesis that the probability follows the Bohm rule. The term Bohmian mechanics is also often used to include most of the further extensions past the spinless version of Bohm. While de Broglie-Bohm theory has Lagrangians and Hamilton-Jacobi equations as a primary focus and backdrop, with the icon of the quantum potential, Bohmian mechanics considers the continuity equation as primary and has the guiding equation as its icon. They are mathematically equivalent insofar as the Hamilton-Jacobi formulation applies, that is, spinless particles. The papers of Darwin Quarter-RRAL popularized the term. All of non-relativistic quantum mechanics can be fully accounted for in this theory. Causal interpretation and ontological interpretation, Bohm developed his original ideas, calling them the causal interpretation. Later he felt that causal sounded too much like deterministic and preferred to call his theory the ontological interpretation. The main reference is the undivided universe, Bohm, Hiley 1993. This stage covers work by Bohm and in collaboration with Jean-Pierre Vigier and Basil Hiley. Bohm is clear that this theory is non-deterministic. As such, this theory is not, strictly speaking, a formulation of the de Broglie-Bohm theory. However, it deserves mention here because the term Bohm interpretation is ambiguous between this theory and the de Broglie-Bohm theory. An in-depth analysis of possible interpretations of Bohm's model of 1952 was given in 1996 by philosopher of science Arthur Fine. See also, David Bohm, Faraday wave, interpretation of quantum mechanics, Madelung equations, local hidden variable theory, quantum mechanics, pilot wave, notes. References. Further reading, John S. Bell, Speakable and Unspeakable in Quantum Mechanics, Collected Papers on Quantum Philosophy, Cambridge University Press, 2004, ISBN 0-521-81862-1, David Bohm, Basil Hiley, The Undivided Universe, An Ontological Interpretation of Quantum Theory, Routledge Chapman and Hall, 1993, ISBN 0-415-06588-7, Dittolf Dar 1/4 Sheldon Goldstein, Nino Zanger, Quantum Physics Without Quantum Philosophy, Springer, 2012, ISBN 978-3-. 642-30690-7, Dittolf Dar 1/4 Stefan Teufel, Bohmian Mechanics, A Physics and Mathematics of Quantum Theory, Springer, 2009, ISBN 978-540-89343-1, Peter A. Holland, The Quantum Theory of Motion, Cambridge University Press, 1993, ISBN 0-521-48543-6, external links, Bohmian Mechanics, Videos answering frequently asked questions about Bohmian mechanics. Bohmian-mechanics.net, the homepage of the international research network on Bohmian mechanics that was started by D. Darwin Quartararo, S. Goldstein and N. Zanger. Workgroup Bohmian Mechanics at LMU Munich, Bohmian Mechanics Group at University of Innsbruck, Pilot Waves, Bohmian Metaphysics, and the Foundations of Quantum Mechanics, lecture course on de Broglie-Bohm theory by Mike Toller, Cambridge University. 21st Century Directions in de Broglie-Bohm theory and beyond, August 2010 International Conference on de Broglie-Bohm theory. Site contains slides for all the talks, the latest cutting-edge DBB research. Observing the trajectories of a single photon using weak measurement, Bohmian trajectories are no longer hidden variables.